Меня зовут Jaroslaw Hryszko. Я очень рад, что я могу здесь говорить. And as I promised that this presentation will be in English, so I represent today a Polish testing board when I work as an advisor in an area of using artificial intelligence in quality assurance. Also, I'm advisor of the board of one of the biggest automotive company in the world. And also I work as an advisor in some non-government organizations, also in Poland. And today I will tell you how we can use machine learning in a quality assurance, in software quality assurance to be precise, but it can be also used in a different applications, not only in one while producing the software. And there will be no science fiction today or during this presentation. I will not tell you about the things which happen currently in a kind of different university in somewhere in USA, for example. I will tell you about the actual cases of using, and I will not stand in the middle of the screen also. Actual cases of using machine learning to predict defect-prone or defective code in practice. That's a kind of surprise. So once again, hello everyone. No science fiction, only practice. And my ambition here is that after this presentation, you will be able to use machine learning, for example, in your own projects, in your companies. Because what I will tell you today, it's actually happening in a different worldwide companies. So it's only a coincidence that I came here from Poland. Let's start with the fact, which is well known to any of you, that the later we will start to fix bugs, to see for defects, to fix defects in a products, in software, the more it will cost us. So from the very beginning of software development, that was this need to see, to check, to know where we should expect bugs, where should we expect defects in software, because the earlier we will know where are our areas in the software which are responsible for defects, for troubles, especially for end users, the cheaper it will be to react. Also, there is a kind of thumb rule from the software engineering saying that for 80% Pareto law in software engineering, for 80% of defects, of bugs, only 20% of code is responsible for. So if we will know this 20% of troublemaking code somewhere here, it will be much cheaper to fix them, to prevent them than before. So in the history of software development, there were many tries to find out where is this most troublemaking code It started with Akiyama's white paper, scientific research, saying that the most of the bugs will be in the longest code, in the longest part of the software, and after that, in '74, McCabe, the guy who invented this complexity factor, complexity measure, said that no, that's not true. We should expect bugs in the most complex code. But in the beginning of 1990s, a guy called Manson published a paper saying that it doesn't matter where those bugs are. We have machine learning, and we can learn, we can teach computers how to recognize this troublemaking code, troublemaking parts of the software, to recognize those parts before the bugs actually will happen. And what Manson proposed was to gather data from the historical releases of the code, of the software, and gather information if some parts, those parts, were defective somewhere in the history, caused some troubles, some bugs, some defects. And when we put it into the artificial intelligence, let's say, in one of the mechanisms of machine learning, for example, classifier, then after we will have a brand new software and brand new data collected from this software, and we didn't yet tested the software. We don't know where to expect our bugs, or in the paths described by this data, or in the paths described by this data, but we have our classifier trained on this historical data. So after we will put the data into the classifier, it will tell us in which paths we should expect defects. And that was Munson's proposal in 1992. So someone can ask right now why we don't use it today in our projects. Well, actually I do, I use it. But why it is not popular? Why we don't have this mechanism, each single one tool we use during the software development, for example, to plan our tests? Because for many years, from this time when Munson written his paper, the machine learning was quite expensive, required very niche knowledge, let's say. And just imagine the situation that we have a project, we have our testers, we have our developers, and we have a fixed budget for the software development project. And then we need to, as a project manager, for example, also include into this already planned project and budget additional people who are, for example, data scientists, to make this machine learning magic I showed you before. So the reaction very often was such that okay, it looks great on the PowerPoint, but we have strict time, we have strict resources, strict budget, we don't have any more for that. And I'll tell you what, those guys, physicians, medicine doctors, let's say, had similar, maybe not problem, but challenge. They already have a lot of data which is very useful from the perspective of machine learning. Because, for example, they have data collected from some kind of diagnostics. And then we can use the similar concept of machine learning, for example, to predict if we will have some cancer cases in the future, right? But, okay, but those people still are physicians, are not, even sometimes they are not technical. They sometimes, well, my personal doctor even struggle with his own personal computer when he needs to, for example, I don't know, write a prescription for me, right? So, in Germany, in the University of Constance, the set of the team of scientists presented NIME, a software which doesn't require any programming skills, any machine learning skills, essentially to make this machine learning I presented to you happen. It is more like building data analysis workflow from bricks. And first of all, it is cheap because the NIME was based on the Eclipse, which is well-known environment for programming in Java. So it is based on the free software license. You just simply build the blocks to analyze the data, and by changing those blocks, you can easily adjust this name to a different conditions. And this is how the NIME looks like. So the team with which I work for, we also had a similar idea that, okay, so if we have similar cases in the software development, that even if we have technical skilled people there, even if we have people who already know about the machine learning, but they don't have time, budget, resources for applying the machine learning in the project. So we thought it would be a good idea to present NIME idea to them. We made some research, and if you are curious, if you Google the name of my humble person in a Google, you will find my white papers describing the entire process, for example, of investigating how much it will cost to introduce NIME in the software development project, and the result was such that it will be extremely cheap to have it. We even added, I don't know if you see it, we even added some additional features to NIME, just to cover the most popular tools, like for example Jira, Bugzilla, HP Quality Center, and so on, just to gather the data from it. And we had successes in different projects, in different companies, with actual applying the machine learning in the process and using it for the quality assurance. I will tell in details about it a little bit later, but still, it turns that we only need 4 hours to use NIME in our projects. 4 hours of training. From the being absolutely, I don't know, green in machine learning usage. But still, we, in many cases, had such reaction from different teams in the different companies or the teams which worked on the open source. Okay, you have the direction was such that you have this NIME, and of course it is a great idea to use machine learning, and everyone tell us right now about the artificial intelligence, but no, we don't have time. We have a very tight schedule, and we don't even have time for that 4 hours. And also, no, you always say that it will take 4 hours, but after that it will take a much more hours. And did you consider the power to power the laptop of on which the NIME is running? Okay, so the next step was that we automated the entire process. So to have this machine learning, to have this training data, once again, details are one slide later. We need different data sources, as you suspect. For example, we need the data from a defect tracker like Jira to know which defects, which bugs we had in historical versions. We also need some data gathered from a source code. And once again, we connected some already being there libraries in Python together. We integrated them, we wrote some scripts in Python, and that's how the adept appeared. Adept stands for automated defect prediction. And then the prediction result, later also I will tell you how it looked like in details, were transferred via some kind of JSON APIs to people who were interested in areas which should turn to be defect prone before we even start to test them. Okay, so what kind of data we need? What is the entire process behind that? It is quite simple, but still we need to follow some special rules. The first rule needs to be followed by the developers, not by the testers, by the programmers. They need to learn, if they don't do it right now, to send to the code repository different changes, like for example, different implementation of different functionalities, or fixes for different bugs, different changes in different commits, because in such way we can recognize due to which causes different parts of the software, of the historical software, were modified. And now it should be a little bit easier to understand. Take a look. Here we have classes. For just the purpose of this presentation, of this example, because we also can have lines of code, we also have methods in different programming languages like, I don't know, COBOL. We don't have classes, we have modules as far as I remember, so we can also have modules, etc. And this example chart presents how many times different, in this example, different classes were modified due to fixing, or as a result of fixing different defects, different bugs. It's not a machine learning, it's just a simple statistics from the historical version of the software, right? So there was some kind of source code, we tested it, and after testing it, we observed some defects, some bugs in the software. So we asked via, for example, Jira, developers to fix them. And they fixed them. And then after obeying this rule and analyzing the change log from the code repository, and connecting the change code information with defects using this relation, that we actually know that particular change was due to fixing defects. For example, when dealing with SVN, with subversion, in many cases there is just a comment there, in which the comment field, in which a developer puts that it was a fix for a C64 defect. This can be considered as a kind of unique identifier from Jira. So by obeying just this simple rule, we can have, and connecting this with the data from the defect tracker, we can have this statistics. Okay, so it gives us a picture how different parts of the historical, once again, historical software caused troubles. And we can easily say that, for example, those classes caused much more troubles, caused much more bugs than, for example, those one. So let's get back to the version of the software source code when we had still not fixed all those bugs in the source code. There is such kind of version, like for example 1.0.0.0.0 or release candidate 1, whatever you call it. But we have this first ever version of the source code where all those bugs are. Of course, after that, once again, we will have the testing and we will see those bugs, and at the end we can gather this data. But still, if we have we are running our version control system correctly, we can have the first ever version of the software, of the source code, where all those bugs still exist, and we can gather data basing on this source code. And in most cases, this data will be source code metrics, different metrics gathered on the source code. There are plenty of different tools which can gather such kind of data for us. Most convenient one to me is also a free tool called SonarQube, because SonarQube has different plugins for a different programming languages. Once again, it is free for most of those programming languages, and we can gather such kind of metrics. And then, if you remember from the Manson example, we can once again decide what we consider as a defect prone. In this example, I only use binary classification. We only have 1 and 0, but we can use different classification. We can, for example, have 0, 1, 2, 3, whatever, basing, for example, on the severity of the bug. But let's just stay that with this agreement that any source code which was modified due to fixing more than 50 different bugs, we consider as a high risk. Anything else we consider as a low risk. Just for the purpose of this example, right? Because in any of your projects, we can put this bar in a different place, or we can, for example, only stick with the critical bugs and filter out other. And having this agreement, we can apply this on these metrics we gathered, and bam. This is exactly the same training, not exactly the same, but this is, well, following the approach I presented you in the very beginning of the presentation. This is how the training sample was created. And then we train the classifier with it in a simplest form of using machine learning for the predicting the most defect-prone areas. And after we will have brand new source code, brand new or no, release, entire release of the new of our software, like for example entire release which was not tested yet, and we, for example, ask for help how to plan our tests. We can present this data describing the brand new software to this trained classifier, as I showed you in the beginning, and then this classifier will, based on this agreement, will tell you where we should expect those high-risk areas in brand new software. Of course, that was the easiest example. If we will work on our classification, on our machine learning a lot, then we eager to use also different pre-processing methods, different tricks to make our machine learning process much more efficient, different classifiers for which, for example, for classifiers based on the neural network, we need to have some kind of counteraction of the case in which we will have just a few ones and large amount of zeros. So we will do some kind of sampling or different sophisticated algorithms. But at the same time, if we will agree on using random forest classifier, random forest works well without any pre-processing. And there is even a white paper, scientific publication, saying that the title was, I believe, do we need all of those classifiers? Because the authors of this white paper tried to convince that the random forest classifier should be enough for any of popular applications of machine learning. And the raw result of this approach looks more or less like that. The list of possible defect-prone areas in the code, and developers already can use it, because for developers, for programmers, it tells something. So going back to this ADEPT, to this automated approach, we had this prediction result transferred using via different network mechanisms like APIs to programmers. And when programmer, in one of the examples, opens the source code file predicted as a defect prone, it will get such nicely looking red bar warning before that we deal with the defect prone source code. Yeah, and one of the hardest questions right now. Okay, so we know that in such areas we should expect troubles, because mighty artificial intelligence, which will kill us all, and apart from that, also will tell us where the bugs are. Told us that we should expect somewhere here defects. So we proposed such kind of sophisticated also methodology to that. Well, it is already published in Polish, and we are currently working on published it in English, so you can fall asleep while working the entire description of the methodology. For now, just I want to tell you that we have this deciding point here based on the defect prediction. That if the file with which we deal during the fixing defect, fixing bug, is on the list, right? What happened? And I gave you spoilers. Shift F5. No, I don't want to. Then we will apply a different code quality assurance technologies. If not, just simple fixing process and we forget about it. Yeah, but what about testers? Still, we have this list of defect-prone parts of the software, of the brand new software, based on the machine learning run on historical version of the software. For many testers, such list is not really useful. So we thought that some kind of dictionary for translating the areas of the code, which would be useful. In many cases, especially if you deal with the Microsoft solutions, there is already automatically created dictionary. If you, of course, use some kind of functions which is embedded in the Microsoft tools. But for example, for some Java projects we dealt with, there is no such dictionary. So we created one as an online tool. It is just a simple online tool, nothing special. Just please notice that we have those predicted areas of source code here. There is a function column in which, for example, system architect can put for which functionalities those suspected areas are responsible for, and then, for example, testers can put nodes here and, for example, decide that we should put high priority on those areas, or apply some special test cases, or apply some additional scenarios, or whatever, or made developers to put some additional unit tests, for example. Or in a different way, if we don't have particular parts of the software on the list, we can, for example, decide to lose a little bit the pressure from those parts and treat it with a less attention, for example. Okay, so that's the entire process in a nutshell. Quite simple. We have historical data describing the historical software. We train classifier. If we are using KNIME, it's just a matter of putting the historical data or reading the historical data by the one block and putting this data to another block named machine learning mechanism, nothing else. We don't even have to know what the machine learning means. The only thing which we should know is that we should put the historical data there, and then the classifier can give us prediction. We started to investigate this approach. Personally, I started in 2012 as a subject of my PhD studies. And of course, we started to also observe results of using this approach. This is one of the results. It is, of course, very hard to answer the very frequent question, how many bugs we omitted, let's say. We don't know, because if we acted proactively by using different techniques, like for example, when developers started to use refactoring on the predicted areas, we don't know how many bugs we fixed before they happened during testing. But we started to observe different factors, and this is, for example, from the performance perspective. When the entire team developed the project, the software version, software release using such approach, using machine learning, we observed that after using the technique, the entire methodology, for example, just by single improvement, we save more than 6,000 of hours for a company by just simple fix. In a different project, we, for example, observed number of defects before, during, let's say, the ordinary way of working, and then we applied machine learning, we applied this way of working with machine learning, and we observe such results. This is quite impressive, because for this particular project, the most important bugs were those found during the system testing. And they managed to reduce those bugs almost by 70%. But my favorite example is this. Making long story short, there is a company who works for another company who produces some stuff. Doesn't matter what kind of stuff it is, in some factories. But thanks to that, or due to that, they have 1 year cycle of software development, because they are only allowed to deploy the software during the Christmas in every factory. So they work by the entire year on a new version of the software, and then during the Christmas they deploy it. So they asked us they started to use the software defect prediction approach, but at the same time they started to observe what they called as support cases. Support cases is a kind of euphemism for a bug on the production, right? And those high priority support case is the most important one, because the defect needs to be fixed within 1 hour. If not, the entire factory will stop. And so this is how the support cases were for the software version developed in a normal way, let's say. And then they deploy the software developed using the machine learning approach. And that happened. During the entire year, they didn't receive any high priority support cases. And we really checked that many times, if this is not a mistake or some kind of lack of communication. Starting from the September, they didn't receive any support case at all. And with this optimistic promise or thing, I want to thank you for, there will be, of course, there is a 5 minutes for questions, right? But if you will have any further questions, you know how to find. Okay, so we have a question.
It sounds to me that as cool as this approach is that this works well for an established large piece of software. If you have a small piece of software and you just started to collect the data, even if you do all the commits well, even if you split out all your, all your bugs really well, you're still gathering the data, and it's not going to be representative of the amount of bugs that you'll find in each class. So this works if you have lots of data already, and if you spent like a lot of time already on fixing those bugs and writing those tests. Does that kind of make sense, or?
Yes, it makes sense. I would put it differently, that it works better for let's say, legacy systems, for major systems, because we have, just like you said, plenty of our own data. But if we want to apply this in a small project, which just already started, there is also a solution to that called cross-project training. Like we, for example, look for a similar project in our company or in other company or in an open source community, but very similar project to ours. Then we train the classifier on the similar project and use the trained classifier in our project. For example, this is the one of the solutions. But yes, I agree that in major projects, in legacy projects, it works much more efficient due to the fact that, just like you said, we have plenty of different data. To be honest, I don't know how this online gizmo for asking questions works.
We have a lot of questions online.
Okay, and just a little time. Do you have plugin for IntelliJ IDEA or other IDE? Long story short, the question, I believe, regarding KNIME. So KNIME is based on the Eclipse. Eclipse is open sourced and based on different plugins. And those plugins are also open source. I have no idea if they have in KNIME plugin for IntelliJ IDEA, but if not, there is no problem with writing one by ourselves, because we can, for example, download the source code for a different plugin and then modify it to use it for our purposes. We did similar thing by creating plugin for the very, very ancient programming language called RPG. Okay, what are main advantages in comparison with SonarQube and FindBugs products? Okay, so it is the old question, static analysis versus machine learning. People like the comparison to, for example, wedding invitation. So the SonarQube and different FindBugs products based on the static analysis looks or they see this wedding invitation or investigate the wedding invitation from the perspective of if the text in the wedding invitation was written correctly without any mistakes. But at the same time, we can do this wedding invitation on the very ugly paper, let's say, or written just on our leg with the normal pen. And still our guests or the people we want to invite will not like it. And having the machine learning approach, we can learn from the previous cases or from the different cases that people don't like wedding invitations which are just ugly. But at the same time, SonarQube and other static analysis products cannot do it. They just look for the correctness of the source code. Okay, the last questions, and then... okay, so if there will be any possibility to get those questions, you can Google my webpage and I will put answers to those questions on the web.
Also maybe discussion during the lunch break or coffee breaks if you offer free.
Of course. So once again, thank you.